So binary erasure channel. Binary erasure channel is given right here in this picture. And there is a input distribution parameterized by pi. So x is equal to 0 with the probability pi. And y is equal to 0 or erasure e or 1. So here is the conditional distribution p y given x. This is about x. X is equal to 0. X is equal to 1. Y is equal to 0. Y is equal to e. Y is equal to 1. So we can talk about probability of y is equal to 0, probability y is equal to e, probability of y is equal to 1, and so on. Since the conditional probability and initial, input distribution is parameterized, we can obtain the expression of distribution of y. So the first one is nothing but pi times 1 minus p, okay? And this one is pi times p plus 1 minus pi times p. So this is nothing but p. How about pi, probability y is equal to 1. So that is 1 minus pi times 1 minus p. Output distribution can be obtained this way. And we can proceed to find the entropy on y and the entropy on y given x. And entropy on y given x is a conditional distribution. So when x is given, the output distribution is this 1 minus p and p. So this one here can be written as with respect to h of p, when multiplied by pi plus 1 minus pi times h of p, and so on. So this one is nothing but h of p. Okay, and h of y, the expression is given right here. So you can have h of y with respect to this distribution. So we can say that entropy on pi times 1 minus p and the p and the 1 minus pi, 1 minus p multiplied and minus and h of p. So we can utilize this result, and then by applying the entropy formula for this triplet, we can proceed that way. But this one is going to give you some tedious derivation, the first term. So we will use some clever way to figure out this first part. So the first part is about distribution of y and the entropy of y. So we will evaluate entropy of y in a clever way. That's what we need to do. So what can we do? We notice that this one is the part that makes some difficulty. So we will utilize a utility random variable. So y has three element, which is 0, error, eraser, and 1. So we will use random variable e, where this is the e, the range space of random variable e, and it has e and no e, no erasure, and no erasure. So when you have 0, no erasure, right? When y is equal to 1, no erasure, erasure is mapped to erasure. So this is your random variable e, okay? Okay, so having defined this, we can talk about joint entropy, is this one, joint entropy, y and e, that can be decomposed into h of y plus h of e given y, right? That can be also decomposed into h of e plus h of y given e, okay, by the definition of joint entropy. And we evaluate this first because of this mapping. When y is determined, e is exactly determined. So there is no randomness on e given y. So there is no entropy. So the entropy of e given y is 0. This means that I can use the rest, which is h of y is equal to h of e plus h of y given e. So I can use this relation, okay? H of y can be decomposed into h of e plus h of y given e. So I can use this, information to drive further. So what is h of e? So h of e, the distribution is p and 1 minus p. So this part is nothing but h of p. And what about this part? So h of y given e. So when e is equal to small e, that occurs with the probability p, right? So, so that's what we need to. That's what we can figure out. And here we have written it down. So the random variable e. So we need to consider this occurs when the e is equal to small e. This occurs with the probability of p, and this occurs with the probability 1 minus p. Okay, and so this one can be decomposed into two parts. H of y given e can be decomposed into two parts. H of y given e is equal to small e, and we need to consider e is equal to small e multiplied, take the product and add it with the other case, when E is not equal to not equal to E, H y given E is equal to not equal to E. So we consider this, and let's take a look at this part. Probability that E is equal to E is P. Okay, so that is P times. What about this one? When E is equal to E, what is the uncertainty on Y? Uncertainty on Y is 0, right? So this is 0, so we don't have to worry about multiplying with the P. And plus this part is 1 minus P. And what happens, what is the entropy on Y given E is not equal to E? Then Y is equal to 0 or Y is equal to 1, right? So that's the entropy on Y. So entropy on Y is basically, and so Y is equal to 0, which is this one, and Y is equal to 1, which is this one, with the probability this. So, and we need to divide it by the sum of the two. The sum of the two is 1 minus P. So the entropy on Y is basically determined to be H of pi, right? Okay, so the conditional distribution P of Y given E is equal to not E is equal to Y is, when Y is equal to 0, that is pi 1 minus P, but divided by 1 minus P I have to do, and 1 minus pi times 1 minus P divided by 1 minus P I have to do. That is when Y is equal to 1. So cancel this. So the distribution is H of pi. The distribution is parameterized by binary distribution pi. So entropy on that is this. So H of Y given E is equal to 1 minus P times H of pi. That is the result. Okay, so what we have is H of Y. Okay, so H of Y we got, which is equal to H of Y we got is H of utilizing this, what we have this derived, basically H of P plus 1 minus P H of pi and minus H of P. Okay, so we figure out that these two cancels. What's left is 1 minus P H of pi. That's the mutual information, and capacity is maximizing this measure, this result with respect to pi. That's what we need to do. And when this is, this is equal to 1 minus p, so or h of pi, the maximum value is 1 because this is binary random variable, and equality is achieved when pi is equal to half. So we notice that this is 1 minus p.